Let's consider the following problem from physics. The name of this problem is coupled mass spring system. In this problem, we will get matrix, we will get a system of differential equation, and matrix of this system will have complex eigenvalues. So the system consists of two bodies with masses m1 and m2, and these bodies are connected with the springs as it's shown at this picture, with stiffnesses K1, K2 and K3 respectively. So the first thing that we do, we denote by x1 the displacement of m1 at a time t, and x2 the displacement of m2 at a time t. And the initial values, we assume that x1 at time 0 and x2 at time 0 both with zeros. So let's write the equations for each body in this system using the Newton's law. So by Newton's law we know that m1 times acceleration, and acceleration, this is second derivative of displacement of the body. This is equal to the sum of all forces which act on this body. And by Hooke's law we know that spring connected to the body will give us the force K1 times the displacement. So, and it's negative, minus K1 x1, and the second spring will give us minus K2 x1. But also m1 is connected with m2, so m2 also will have the force which acts on m1, and K2 contains the force m minus K2 m2, and it's negative force for m2 but it's positive for m1, so we will get plus K2 x2. So you can think, in fact, you can try to find similarity with the tanks connected with pipes. So if m1 is one tank and m2 is another tank, you see that these two springs will give us output of water, and this body m2 with the spring K2 will give you input of water. So the output will be K1 x1, K2 x1, and the input will be K2 x2. And similarly we can do for m2 x2 second derivative. We have the outputs minus K2 x2 minus K3 x2, and the input from the body m1 plus K2 x1. So we have this system of linear differential equations with constant coefficients. So you see that the first thing that you can notice that here we have second derivatives. So this system is not in normal form. So the first step is to write this system in normal form. Okay, let's do this. So first of all, let me write it as just taking out x1 and x2 in these equations to make it more beautiful, and then we will write it in normal form. To do this, we have to introduce, let's say, some new vector y, which will have 4 coordinates, because we have both of the functions x1 and x2 are involved in second derivative, so overall we'll get fourth derivative, right? So therefore we'll have 4 coordinates, and we denote y1, let's say this is x1, y2 x1 prime, y3 this is x2, and y4 is x2 prime. So let's write the system in normal form. So y1 prime, first we have to write y1 prime is, y1 is x1, so y1 prime is x1 prime, which is, x1 prime is y2, so which is y2. y2 prime is x1 double prime. And from the first equation, we can find x1 double prime. This is minus k1 plus k2. We have to divide by m. x1 plus k2 over m x2. And now we replace x2 with y1, x1 with y1, and x2 with y3. So this is minus k1 plus k2 m x1 y1, sorry, plus k to m y3. y3 prime is x2 prime, which is y4, and y4 prime is x2 double prime, which we can find again from the second equation, which is k2 over m x1, and x1 is y1, minus k2 plus k3 over m, which is x2, and x2 is y3. So we get the equation y prime is ay, where A is 4 times 4 matrix. Let me write it. So in the first we have only 1, 1. On the second place, in the second equation, we have two coefficients. In front of y1, we have minus k1 plus k2 over m. For y2, we don't have any coefficient. For y3, we have k2 over m. For y4, we have 0. The third line, we have 0, 0, 0, and 1 on the y4, so on the last place. And here we have coefficients k2 over m, y1. Again, we don't have y2 here. And for y3, we have, okay, how we can write it, k2 plus k3 over m. And again, no coefficient for y4. So this is a matrix that we obtain. And the solution, so the eigenvalues, you can check that eigenvalues of A are plus minus I sum beta 1 and plus minus I beta 2. So there are 4 eigenvalues. They are all complex, and they are all have only imaginary parts, no real parts. And in fact, these two numbers, beta 1 and beta 2, are similar to angular frequencies, and therefore the numbers, let's say nu 1, which is beta 1 over 2 pi, and nu 2 is beta 2 over 2 pi. These are frequencies for this two-body, and they called natural frequencies of the system. So these are natural frequencies. So let's now look at an example. For example, let's find these natural frequencies for this particular case. M1 and M2 are 1s, and K1 is 1, K2 is 2, and K3 is 3. So let's firstly write the matrix A of the system, where A is, so this is 0, 1, 0, 0, and M1 is 1, right? So K1 plus K2 is 1 plus 2 is 3, so minus 3 here. 0, K2 over M1, K2 is 2, 0. Sorry, it should be 1 somewhere. Yes, at the end. Just forget to write it. So 0, 0, 0, 1. And here we have K2 over M2, again 2, 0. K2 plus K3, this is 5 with minus and 0. So the matrix A in this case has this form. So what we have to do to find normal frequencies, we have to find eigenvalues of this matrix A. So we have to find the determinant of this thing, which is minus r 1 0 0 minus 3 minus r 2 0 0 0 minus r 1 2 0 minus 5 minus r, the determinant of this thing. So determinant of 4 times 4 matrix is not so easy task, so let's maybe try to find a way to make it easier. So we can choose the first row, for example, and write the following: minus r times the determinant here. So minus r times the determinant here, minus r2 0 0 minus r1 0 minus 5 minus r. And also we have 1 in the first row, so this is minus 1, minus because we have second column in the first row, the sum will be 3. Therefore we'll have minus 1 to the power 3 is minus 1 times the determinant of this matrix. If we cross these two column and row, we'll get the matrix which is left, minus 3 2 0 0 minus r1 2 minus 5 minus r. So the determinant. And of course we'll get the equation of degree 4. And if you open this, you can check that this is r4 plus 8 r2 plus 11. This must be 0. So we must solve this equation to find the eigenvalues. So this is just quite standard thing. We replace, let's say, t is r square, and first solve t square plus 8t plus 11 equal to 0. And in this one we'll get t1, t2 is minus 8 plus minus square root of 64 minus 44. 64 minus 44 is 20. So we divide everything by 2. So we get that t1 and t2 are minus 4 plus minus, and square root of 20 is 2 square root of 5 plus minus square root of 5. So what we can notice that they are both negative, right? So it means that r will be complex numbers. So r1 and 2 will be plus minus square root of minus 4 plus square root of 5, and r3 and 4 will be plus minus 4 minus square root of 5. So our betas now, beta 1, this is coefficient of I. If we take I out of this, we'll get square root of 5, square root of 5 minus square root of 5 plus 4, and beta 2 is square root of 5 plus 4. So we get these two frequencies.